Hi, so I'm Brandon Joel Gonzalez, and my teammate is Zhuo Cheng, and this is 18843, Mobile and Pervasive Computing. This is our project, improving LPWAN performance using directional antennas. So for some background about this project, essentially, what is an LPWAN? It's a low power wide area network, such as LoRaWAN. That's a very popular one and the one that we use for this project. It is used as a popular form of wireless network for IoT, so the Internet of Things. It provides a very strong advantage in terms of power consumption. They're designed to operate for years on end, and it also covers a wide area. But there are some issues with LPWANs when it comes to network capacity and interference between nodes, and so what this project tries to do is it tries to leverage directional antennas to essentially reduce the interference between nodes in the network. And so this is called, using directional antennas for this purpose, this is called nulling. And so using nulling allows you to focus your energy in a specific direction towards a gateway in the network. And this hopefully would provide better improvements in the interference between nodes in the network. You can see sort of just the network architecture for LoRaWAN to get a better idea. Essentially, in a LoRaWAN network, you have the clients or the end nodes. Here is a LoRa node, and you might have network interferers that aren't necessarily nefarious, but there exist lots and lots of networks and devices in these networks. They are communicating wirelessly using LoRaWAN, which is a network protocol, uses a type of modulation called chirp spread spectrum. It essentially communicates to gateways, which are just listening for packets. And once a gateway receives that packet, then it'll transmit that to the server. And we use what's called a chirp stack for the server. It uses MQTT to listen to messages. So this LoRaWAN gateway, note that a node might, it just broadcasts out a message, and it might actually receive the same message at multiple gateways. So it's up to the gateways to essentially, they'll get some information about the packet, such as the received signal strength indicator and the signal to noise ratio, and then it can communicate that message and that information to the server.
Okay, hi. So our implementation is based on some hardware and software from Dr. Arthur. He's a previous PhD student from Vice Lab, and we got this antenna hardware. We got this directional antenna hardware from him, and each of those antenna is like a omnidirectional antenna. But we combine those two of them and using some phase shifting stuff we will explain later. And by combining those two, we got a directional antenna. And also we run 4 gateway across the CMU campus, and you can see their locations here. And they are at the CISA first floor and the rooftop of the wing hall, the rooftop of the personal hall, and the rooftop of the East garage. And we run like the server in Python, and those server would collect the signal sent from this antenna. And when this LoRa antenna starts, this node would circle through its nonlinear patterns. It has like 4 nonlinear patterns. The phase shift would be like 0 degrees, 19 degree, 108 degree, and 270 degrees. And it would circle through those 4 different nonlinear patterns. And those gateway would track, and those gateway would see the SNR, like, which is the signal noise ratio. And in the end, like, this antenna would choose the best configuration, which the configuration which gives the best signal. And yeah. So first, we will show some simulation results based on some math model of the signal strings. And you can see this graph shows like the signal strings for different directions from 0 to the whole circle. And this is like those two antenna use the same phase, and you can see like the signal strings is stronger towards 0 degree and 108 degree, and we can gradually change the phase, and you can see the difference. And so now we gradually change the phase, and you can see that the signal strings it changes according to when we change the phase. Yeah, so the general idea is that if we change the phase between those two antennas, like the strongest, the direction which has the strongest signal will change. So by using this idea, we can by choosing the phase, by choosing the phase between those two antennas, and we can make sure that we send the signal towards the gateway.
The basic idea, as Zhuo said, is that we can introduce different phase shifts to each of these antennas and steer the main lobe of this device in a particular direction. So how we try to find the best nulling pattern is we essentially just cycle through all of the nulling patterns at first. So we pick a nulling pattern, we send a few packets just to see what are each of the gateways going to get. In particular, we're interested in the signal-to-noise ratio because we treat interference essentially the same as noise in the network when it comes to RF systems. So with that in mind, each of these gateways, they're going to get the packets, and then they're going to see what's the SNR. Once the node kind of cycles through all of the different packets, and that's what we can see in the first part here, where we're basically just, on the server side, we're printing out all of the packets that we're receiving with the different antenna patterns. Once we've done that, then we can make a decision and say, okay, based on the SNR values that we received at the gateways, the best nulling pattern is this one, and it can choose one of the four nulling patterns. It'll choose whichever one and then start broadcasting in that direction. Then what we do to kind of get a good idea of how good is the nulling working, we have an interferer here. This is just a whip antenna that's connected to another one of these cube cell devices. It's connected to a whip antenna. And this broadcasts omnidirectionally, so it doesn't steer it in any particular direction. It's just kind of radiating outwards. So we basically we let it run for a little while, and it's collecting packets. And at some point, about halfway through the run, we turn the interferer on, and we see, okay, let's see how the interferer impacts the SNR. Then we can kind of move the interferer around, or we can disconnect the interferer and see how the SNR changes. So that's what we kind of do. We are logging the SNR values, and then we essentially plot them. So just to kind of explain what's happening in this plot, we're plotting four lines, and they are the SNR values for the packets received at each gateway. So in blue, that's at the CIC. In green, we see the gateway on Posner Hall, and then in red, we see the gateway at the East Campus Garage. So as you might expect, the East Campus Garage, that is, from where we are in campus, that's on the other side of campus, and there's a lot of attenuation as it travels through buildings. So as we expect, we're getting a pretty poor SNR. You can see it's dipping towards -20. What's more interesting is what we're getting at Posner Hall in green and at Wien in green, or sorry, Wien in yellow. We can see the SNR that we're getting. Around this point is where we turned on the interferer, and we can see the SNR values dip. We can see a dip once the interferer is turned on, and then once we disconnect the interferer, we see the SNR values kind of go back up. Because that's what we expect when we turn on an interferer. It's interfering with the signal that's being propagated, and then once we remove the interferer, we see the signal to noise ratio improve.